In the next few videos, we're going to start discussing the rules of indices. Indices are basically powers or exponents, and certainly if you are checking out different textbooks for extra examples, these might be alternative definitions for indices. We're going to start off by looking at rule 1. And we've got a to the power of m times a to the power of n. Now, the two a's are just what's known as bases. And so long as the bases are both the same, we can work and combine these two together. Now, example that we can work with, if we have a to the power of 3 times a to the power of 2, a to the power of 3 is just another way of writing a times a times a. Whereas a squared is just a times a. Now if we multiply these two together, we now have 1, 2, 3, 4, 5 of these a's being times together. So this could be rewritten as a to the power of 5. So a cubed times a squared is a to the power of 5. What we can see then is we've added 3 and 2 together to give us 5. A second example, just to be sure that we know what we're doing here, let's see if this works if we have c to the power of 7 times c to the power of 3. Now, if it follows the same rule, then 3 plus 2 is 5, then hopefully we should get 7 plus 3 gives us 10. We are hoping for c to the power of 10. Let's just see if that works then. So c to the power of 7, that is just 7 c's all timesing each other. 4, 5, 6, 7. And c cubed is just c times c times c. So we've now got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C to the power of 10. So what I can say, if I've got a general rule, a to the power of m times a to the power of n, all I'm doing is just adding those two indices together. So this would give me a to the power of m plus n. This is the first rule of indices and is the basis behind the majority of the rest of the rules. So some quick examples then, just to make sure I've got a bit of practice here. We've just done this one with c. We'll do the same with q though. Q to the power of 7 times q to the power of 3, q to the power of 10. R to the power of 9 times r to the power of 13. 9 plus 13 is 22, so r to the 22. And then it gets a wee bit trickier because we now have big numbers, coefficients, in front of the b's. These still times normally, so 4 times 3 gives us the 12. 4 times 3 is 12. The base still remains the same. We still have a b in there, and now we have to work out what the power is. We've got b to the power of 13 times b to the power of negative 2. Well, 13 plus negative 2 is the same as 13 minus 2, which gives us 11. So this is 12b to the power of 11. In example 4 here, we've got 5m times 2m to the power of 9. Well, again, the coefficients 5 times 2 gives us 10. We must keep the m there. Now, this is a bit trickier because we're not told what the power is here. But as with the majority of algebra, if there is no power told as part of the question, we must assume it's the power of 1. So 1 plus 9 gives us 10, 10m to the power of 10. This also works with fractions as well. If we've got y to the power of 1/2 times y to the power of 3/2, well, we know the denominators are the same, so the denominator will remain the same, y something over 2. If the denominators are the same, we just add the numerators. 1 plus 3 gives us 4. Now, this fraction here can be simplified down. 4 divided by 2 gives us 2. And our final example I want us to see is what happens if we've got two bases that are different. So whereas before we've got bases that are the same, the base remains the same. In this one here, we've got x to the power of 7 times t cubed. Because the letters are different here, we just list them one after the other. X to the power of 7, t cubed. We do not combine them. This is not the same as xt to the power of 10 or x to the 10t or any variation of that, okay? We just list them one after the other. This is one of the most common mistakes we see. Do not fall into that trap. And there you have it. Now try some examples for yourself.